My name is Brian Ellis, Micro-G Lacoste. This presentation was put together by Derek Van Westrom, who used to be an employee at Micro-G. I've changed it up a little bit. I feel like he still should be kind of noted on this as well. So we're going to go over today specifically the FG5 X, quick specifications of it, 2 microgal accuracy. That means if 2 of the same instruments measure at the same point, they should agree to within 2 microgals. Does everybody know what a microgal is? Maybe I should back up a little bit on that point. So 1 gal is a centimeter per second squared, some random unit. And so then a microgal is 10 to the minus 3 gals. 9.8 blah, 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 out to 9 decimal places, basically. So like at Micro-G, our gravity number is 979,632,920 point something. And we can get to that 920 or 929, sorry, 919, plus or minus 2 microgals. So that's give you an idea of how far out it goes. Precision at a quiet site, everybody asks, okay, what's a quiet site? We have isolated piers at Micro-G. Unfortunately, we just had a food manufacturer move in next door with some big grinding machines to make hummus, so that doesn't help. But typical site with the 10-second drops, so you're taking a measurement every 10 seconds. You should be able to get about 15 microgal per square root hertz. I'll explain how we get that number a little bit later. Basically, you can get to 1 microgal in just under 4 minutes. If you keep going, you can get down to smaller precision. The question is, how precise do you need? And also, it matters how noisy your site is. Nice thing is, operating range is worldwide. You can measure at the top of Mount Everest or the bottom of Dead Sea or wherever you want to go. Here in Baton Rouge, that's below sea level. And you don't have to re-range like you do sometimes on a relative meter or anything like that. Operating temperature, we say 15 to 30 C. The FG5 is definitely a laboratory piece of equipment. It needs to be humidity controlled, ideally, good AC if you're in a humid environment, and then also temperature. The piece of equipment that's the most temperature sensitive is the laser. It can't get too hot or too cold. It'll just won't work as well. The dropper, if it gets either too hot or too cold, it also can have some issues, but the laser stops working before the dropper stops working. So we're kind of limited by the temperature range of the laser. And then, like I mentioned, humidity controlled. There's optics, we kind of mentioned that earlier. You gotta be careful, taking cold optics out into the hot, humid environment. You're gonna get condensation. Our electronics also aren't, we do what we can to keep them environmentally safe, but the boxes aren't sealed, and so a lot of times we'll see equipment come back from super humid environments like Thailand or something like that, and we do see corrosion on electronics. So if you're storing it, store it in a humidity controlled environment. If you're measuring, measure and then bring it back into the controlled environment. I should also mention, at any time, if you guys have questions, chime in, please. It's very informal, and this is for you guys, so if you're like, wait, I didn't quite catch that, what was that? Basic principle of operation, we've got a vacuum chamber. This is our apple, if you will, Newton's apple. Basically just drop a test mass, it falls. We've got an interferometer, which takes care of the distance, like the interferometer basically measures the distance, and then the lower stationary mirror, this is what we consider the super spring, just does ground isolation. So as that mass is falling, if the ground is also moving up and down, you're gonna see that in your in your measurement, right? So if the ground moves up as it's moving down, it looks like gravity is higher, and vice versa. If the ground moves down as it's falling, it looks like gravity is lower. So this helps us isolate that and take out not all, but most of the ground noise. Oh, live slide. So you can see here the beam comes in, half of it gets reflected up, bounces off the test mass, the falling test mass, comes down through the super spring, gets reflected back up, and then the other half goes straight through to our detector. They get recombined, and I'll show you in the probably next slide. Free falling, we get interference between the two different paths. There's lots on this one, awesome. Got to be in a vacuum, so that any residual molecules that it runs into is going to slow it down. It's going to make gravity look less. Yeah, and then the interference, I'll show you here what I mean by interference. Light travels in waves. If you change if you get same wavelength, the same path, the waves are always going to be in the same orientation. If you bounce it off like here, as this guy falls, this path is going to get shorter and shorter. We can see that change when we compare the two signals. Right? So if they're in sequence, they have constructive interference, and we get large fringes. If they're out of sequence, 180 degrees out of phase, we get nothing. So we can see here, this is basically the amplitude of the fringes. We get high fringes, 0, high fringes, 0. And that's just from the wavelengths interfering with each other. We record the time with a rubidium oscillator.
Where is that?
It's located in the SIMX. And the timing signal comes out and goes to the card. Every time we see basically one of these fringes, the zero crossing, we know that the path has changed by half a wavelength, right? So to go from min to max, you can see that this one has to travel half a wavelength. Every time we see one of those fringes, we record the time, and that gives us a time distance pair every half wavelength as the test mass drops.
You state that what you're seeing is a higher frequency because the mass is accelerating.
Correct. Yep, exactly. So we get our time distance pairs get closer and closer together. You can use math. The computer does it all. It's great. And that's how we get our G value. That's a good point. Yep. That's why they're getting closer and closer together. So and here's the math, right? So for every fringe, half of x, we measure a x and a time, plug that. This is our kind of the standard equation everybody's used to seeing for distance. We also add in a few more terms because we want to be more accurate. We want to get a microgal. Some of those terms include the gradient, the vertical gradient. So as you get closer to the Earth or more mass, the gravity actually changes, so it's not linear. It's roughly 3 microgals per centimeter. So if you measured 1 centimeter higher, it's going to be 3 microgals lower. We also take into account the speed of light. Not my expertise per se, but so I can't answer too many questions about that, but I know that it's basically a Doppler effect as the light bounces up and you're traveling into it versus away from it.
That's a tiny term.
Yep. Initial position, we start at 0, so that kind of goes away. The initial velocity is, in this case, 0, that goes away. And then the initial acceleration, g0, is what we're looking for. So we solve this big long equation for xi, ti, for however many fringes you want to sample, and we get g out.
So if we're solving for the initial, so the point that we're solving for gravity is at the top of the drop.
It ends up being the effective height is about 1/3 down from the top of the drop. Quick schematic. This is the old FG5X, so it looks a little bit different inside, but you guys can look through the glass and see there. We've got a free-falling corner cube inside the cart, drag-free chamber inside the vacuum chamber. I'll explain what I mean by drag-free chamber here in a second. The ion pump to maintain the vacuum. The interferometer, and I'm going to go through all these in more detail, each section. Photodetector that measures the actual fringes. Super spring, which isolates. It's basically a servoed coil with another corner, we call a corner cube, retroreflector, and then support stuff down below. All this is just structure, leveling tripods and structure to hold the dropper. These are kind of subsystems that I mentioned there: dropping chamber, interferometer, super spring, laser, electronics, software. Just kind of outline of what I'm about to talk about. Dropping chamber, so a drag-free cart. Inside there's the test mass, and then it's kind of surrounded by that cart. The reason why we do that is because no matter how good of a vacuum, well, we don't get down to super high vacuum, right? It's good enough vacuum. There is going to be residual molecules in there. If you have that test mass inside a cart, everything around it is moving at roughly the same velocity and acceleration. It reduces the error due to residual molecules, basically. It also reduces the error due to static charge. So it's floating, so there's no connection, and it's in a vacuum, so there's no way to dump static charge. So if it somehow builds up static charge, the cart at least is moving with it, and the stuff that's very close has less of an effect on it because it's moving with it. We're getting into it. Follows the dropper. The cart, so there's test mass, cart falls out from underneath it, the test mass falls, cart slows down, catches the test mass, and then hits the brakes. Helps reduce any wear on the test mass itself. Shields, like I said, shields from electrostatic force. And then also inside the dropper, the FG5X has recoil compensation. You'll see when we get to the dropper, you'll see two carts on the outside, and as the main cart goes down, they go up. And that just equal and opposite force. If you're trying to shove something down really fast, everything else has to lift up, but if you have compensating masses, reduces the amount of impulse you put into the ground, which eventually could get into your reading.
I presume the bottom of the chamber is transparent?
Yeah, there's a glass window underneath that the beam goes through. The corner cube, or the retroreflector, it's a piece of glass with a reflective coating on the outside. The beam shines up and in, and the geometry of it makes it so that any beam that goes into it comes out parallel. So even if it translates, you can see how the input beam is hitting way further out. It still is parallel, it just gets translated the other way. Same thing with rotation. As you move it, they're crazy. If you look at it, you always see your eye because it comes right back. And even if you rotate it like that, it keeps following you. Insensitive to translation and rotation, used in both. It's both in the dropper and the retroreflector on the bottom. And that keeps the beams that are reflecting off of it parallel and vertical. Test mass itself, this is kind of a 2D representation of obviously a 3D object. You could consider this middle ball and V pushed into the page, so it's basically three points that get caught. And also they're not actually on the retroreflector, there's structure around it as well. Tungsten parts, they wear out every time you drop. These parts hit. The nice thing is it reoriented the test mass after every drop, so you're ready to drop again. You don't have to do something fancy to be ready to go. But they do wear and hit and bounce, and so we say probably about 500,000 drops to maybe 1 million drops. The balls and V's are probably not what's going to go first. The ion pump has a limited life, as well as there's a mechanical feed-through, and that's probably 3 to 5 years on those. If you leave it on vacuum, that's one way to help save the ion pump. So the hardest part for the ion pump is turning on, like catching the vacuum. So once you get it there, if you can try and leave it on, it'll last much longer.
So we want to make sure that we've got an uninterruptible power supply.
Correct, yep. That power supply that is on it does, like I mentioned, have a battery in it. So you can unplug it from the wall, just leave it on, unplug it from the wall, move it over, plug it back in, and you're fine there.
But
probably
on occasion on campus, especially Christmas holidays, sometimes they'll cut off power for more than a day.
Okay, yeah, then probably needs some type of UPS for storage. If you know it's going to be a long time before you're going to use it again, so say several months, then you probably want to turn it off. But if it's going to be,
That shouldn't happen here.
okay, you guys are going to use it a lot, week to week for sure. It sounds like. Speaking of ion pump, I was explaining a little bit earlier. You know, there's molecules inside. Ion pump is basically two plates that have a 4,000 volt potential. So ground plus 4 kV. When you turn it on, it rips apart, rips the electron off, gets plated into the positive kV side. Sometimes it potentially might run into another molecule, which will then spin off another electron. And it's just kind of this chain reaction of plating electrons one way and everything else the other way. The nice thing is it's kind of a black box. As long as you've got 4 kV on the indicator and low current, it works. So, the current is proportional to the number of molecules being ionized. So if you see, whatever you see the current on there, that indicates your level of vacuum. Lower current, better vacuum. The vacuum level has to be 10 to the minus 5 before the pump can even be started. And then like we're doing right now, it's, you start with the turbo pump. And this is, they say about 5 years. But if you keep it on, I mean, we have A10s that, our survey guys take care of, and they get a new ion pump maybe 7 to 10 years. So if taken care of, they last for quite a while. Talk about the interferometer a little bit. We saw this picture earlier. This is a Michelson interferometer. We actually have a little bit different. We do a Mach Zehnder, and that's just so that we pick off the signal coming back up, and it's easier to align these two beams when they come back in. This one here will translate this beam up and down, and this one here will steer it in this orientation left and right on the page, actually in and out of the page as well. So this will do overlap, and this will make it collinear. Yeah, parallel and overlapped. So basically, if you have your two beams, if they're not overlapped at all, you get no fringes. If they're half overlapped, you get some fringes. And ideally, you want them perfectly overlapped as well as perfectly parallel. So the only reason why we do a little bit different here is in order to do that. Very colorful representation of the interferometer. You can see the fiber input here. Beam comes in, hits this first beam splitter. Half of it goes straight through. The other half goes up, hits the dropper, comes back down, hits the super spring, gets picked off here with this little mirror. This is what we call the twiddler. That is what makes it overlap. And then this mirror here steers it so that it's parallel. Recombines in this beam splitter again. We do some beam splitting of it here so that we can come out the viewport. The viewport's missing in this drawing, but there you can optically, just by eye, kind of tell what the fringes are doing. It's best to use the fringe output to align everything, but you can kind of do rough alignment using the viewport there. Rattles around, hits another mirror, comes up. This telescope is for checking beam verticality and alignment. And also kind of hidden back there is another piece of the beam hits the photodetector, which actually does analyzes the fringes. Two signals come out. We have an analog signal for alignment, and then the TTL signal which is just basically a square wave pulse signal for the actual timing and measurement of gravity. So the only adjustments that really need to be done on the interferometer input beam, there's a mirror mount where the beam comes in, and that's to make the beam vertical. The reason why it's important for the beam to be vertical is so that you measure that component, the only component of gravity, right? Gravity straight down. If your beam's at this angle, you're going to measure some cosine of gravity. So You gotta make sure your test beam is vertical. The twiddler I mentioned, that's this guy right here, takes care of, makes the beams coincident, and then the mirror underneath makes them parallel, and finally you gotta align all those beams onto the photo detector. That's all done here, that's all done at the factory, but there might be times where you need to make little tweaks to make sure your fringes are good, or every time you set up, you have to make sure beam's vertical. Alignment on the photo detector itself, less often, and these two you do almost every setup as well. Kind of better example of the beam path. We talked about all this telescope. To check beam verticality, you'll see the difference is we put in the alcohol pool. So it's basically just a jar of alcohol. The reason why we do that is the face of the alcohol pool is always perpendicular to gravity. No matter how you tip it or where you are, it's always, even if you have a huge mountain on this over here and you got a lot more gravity on this side, so your gravity vector is actually going to be pointed towards that mountain a little bit more. You will always, that face of the alcohol pool will always be perpendicular to the gravity vector. Bounce it off, comes back, goes back through. Basically, if this line that comes up hits the dropper, again, remember, if it goes through the retroreflector, it comes back out parallel. If those two lines are parallel and you see one spot in the scope, then you know that your beam is vertical. Let that sit in for just a second. Why is that? So if this face is always, your beam is vertical to gravity, parallel to gravity. If this face is always perpendicular to gravity, and let's say you come in at a really sharp angle, you're going to bounce out at a really sharp angle, and you won't see two spots when you come back into you will see two spots when you come back into the telescope. If it hits and it bounces straight back on itself, you only see one, and that means it has to be parallel to your gravity vector. Well,
Now, the laser beam is supposedly hazardous.
yes. At
So
certain.
So you're looking at the laser beam straight on, so why isn't it hazardous?
At this, by the time it gets through here, that's part of the job of this as well. So we call this the rattler. It bounces back and forth through that and loses a lot of power. So coming out of here,
It acts like a filter.
yeah, all of this really acts like a filter. Coming out of the laser head itself is probably 120 microwatts, which if you looked at it for too long would make you go blind, absolutely. It goes through a bunch of other optics, the fiber optic cable, and by the time it gets here out of the fiber optic cable, you're probably looking at 25 microwatts, which you shouldn't look at. It's not, it won't blind you, and you'll want to look away before it does any damage. And then by the time it gets to the end of the telescope, it's very dim. You can look at it all day if you want, and there's no issues there. Yeah, when you have the alcohol pool in there, it doesn't go through the twiddler or the paralyzing mirror. So you can be confident that those don't affect your beam verticality. Any other questions about this one?
The parallelizing mirror, there's two screws. Is that these things here?
Nope, these are beam blockers.
Okay.
So inside here, the twiddler's in there. It's actually held on by that. You can see this screw right there is that screw.
Right.
So when we get it up on there, we can play with it. This mirror can be rotated this way, right? So it can pivot on that screw, or it can also, that thumb screw can be turned and it spins in its mount in the other direction. So you have total control there. The paralyzing mirror is underneath the scope back here, and it's just a three screw mirror mount. Very similar to like this one,
Right.
but instead of holding a fiber input, it holds just another mirror that it bounces off of. So here, the only thing that controls beam verticality is this fiber input stage. So that's all you have to do. When you're checking verticality, you only have to play with this one. Then once you set that, you take the alcohol pool out and you bounce back through the twiddler and the paralyzing mirror. This will stay vertical, and now you just get your beams, when they recombine here, you get your beams to be coincidental and parallel, overlapped and parallel. And then we just split it off, go to the photo detector, go out to the scope. And the one thing that's not in here is that it also goes out to that viewport that sticks off the side out here. So yeah, it's very safe to look in that end of the scope. So. Any other questions there? Talk about the super spring real quick. Roughly 60-second period. It's a 2-stage nested spring, so that there's the outside world, and you could basically hang one spring and then hang another spring and control the bottom spring. Sphere detector just for positioning, so we shine a light through a sphere, and then we can see up and down position on a detector on the other side. And then we can control coil transducer, so there's a magnet and a coil that we feed back that positioning and hold the retroreflector very steady. And you can walk around and you can stamp your feet, and it adjusts as it needs to, so the outside world's moving upside down, or like moving up and down, and the reflector is staying very, very still. So on the FG5, there isn't temperature compensation. That's only on the A10. In that case, there's actually a little, I take that back. There is on this one. There's an aneroid that as the temperature goes up, it adjusts. That there's basically a oil well, and the reservoir expands and it moves it up, so that as slight changes in temperature will keep the test mass in operating range. We also have a motor for spring height adjustment. Over time, the spring itself will sag just due to weight staying on the spring. There's a 0 function. You hit the button, it puts it back in the operating range with the little motor. Bubble levels to tell you how it's level. I mean, if you hang a mass off a basically it's a pendulum, and you get it too far over, it's going to swing over and things are going to drag. So those are on the outside of the super spring. Those are set at the factory. Hopefully those don't get off level. If they do, then unfortunately it does have to come back to micro G. There are some ways that we can, there's some advanced techniques that possibly, but that should be a very rare would you need to adjust the bubble levels on the super spring. So talked about the delta rods. I'll show you a picture here in just a second, and I mentioned the zeroing of the sphere position. You can see inside here is where the corner cube is. So the beam comes down through the middle, through this tube, bounces off and comes back up. The outside structure is held up by delta rods. You can see one here. It's actually a triangle plate, delta rod here, and then one on going back into the page and one going back into the page, as well as another one up here on this plate. There's 5 total delta rods. If we had 6, it would be over constrained and it would jam up. These hold the main spring, which have been removed in this picture. Sorry, not the main spring, but the outside structure springs. And then the inside spring, the second stage is in that tube. It goes down the middle and the beam goes right out, like right around the spring. It's kind of a representation, shows you a little bit better. You can see the 2 outside springs. They hold up a structure that holds the main spring. The aneroid's on the outside here, and it adjusts basically the height of that connection point up and down so that our sphere stays within the operating range and the coil magnet pushes the second stage up and down. Probably a little more detail than you need, but you see how it works. This is what the spring does. So without the spring, you can see, I'm not sure where this is, probably pretty standard. Our precision is plus or minus 163 microgals. You just see the drops are all over the place. Each one of these little dots is a drop. With the super spring, we're looking at plus or minus 8 microgals. And this is the same location, just with the spring on versus the spring off. This goes back to, how quickly can you get to 1 microgal? Obviously, would take a lot longer if it was actually 163, much quicker to get to 1 microgal precision with 8 microgal drop scatter. The laser is a primary standard. It's as we talked about before, a stabilized iodine cell. Accuracy to 1 part in 10 to the 11th. So in this case, we say we're part in 10 to the 9. So it's not our limiting factor. It's way better than it needs to be, but it's easily, it's a laser that we can get our hands on. And like I said, a visible laser, which is nice. The guy that makes them works just down the road. So for lots of reasons, it's very adequate for what we're doing. We add a fiber launching system, which includes Faraday isolator, 5-axis stage to steer that beam into the fiber, polarized fiber to help get the beam to where we need it, and then we have a collimator on the end of the fiber, because when the light comes out of the fiber, it just sprays out, and we want it to be nice and parallel light all the way through. And then, like I said before, this is kind of our limiting factor is the operating range of the laser. Cartoon of the laser, if you will. There's a helium neon cell up front that actually does the lasing. You excite that, it goes through an iodine cell to a photodiode, and that's basically where you get the laser power out the front. And you can also, the electronics monitor that for the dips in power when you excite the iodine cell. If we get to it, these are really the 2 places that need to be cleaned. You take the lid off and there's an access hole that you can get to these 2. We'll try to get to that for sure, especially with with the humidity here in Louisiana, going from AC to humid environments, you might build up some condensation on the laser, and that might be something you have to do from time to time. If you notice that your power is just dropping, you just get in there with a little bit of alcohol, wipe that surface clean, and it should be good to go again. Talk briefly about electronics. Basic overview. We'll have a computer. In this case, it's a laptop now. The SIMX is where everything is controlled, the super spring and the dropping chamber, as well as...
What's SIM stand for?
I don't know.
System Interface Module?
Yes, there you go. It's been a while. So it used to be the SIM. You'll see the white ones on some models. Now with the FG5 X, we went to the SIMX. Much more robust system and just better all around. Everything's inside one box. There used to be power supplies in a separate box, dropper controller in a separate box, super spring controller in a separate box. Just kind of got all integrated into one. Rubidium clock is in the SIMX. The pressure sensor is in the SIMX. Yep. The Xbox is a PCI unit. It just expands the computer. We used to have full-sized lunchbox computers that those computer cards could fit into. The timing card is still a big card that we can't shrink down into the laptop. So that's a specialized card that just only one place makes it that does what we need. Just going to go through kind of some of the connections. You got to connect the computer to the Xbox. USB digital trigger out, so there's also a cable that goes to the SIM-X, and that controls, the computer tells the dropper to lift and drop. The SIM-X tells the computer, gives it the TIA trigger and the fringe. It says, okay, I'm dropping, measure fringes, here's all the fringes. Where'd that one go? The Xbox has triggers up to the dropper, tells it to lift and drop. Fringes come back to the computer, actually go through the Xbox to the computer. The timing goes up to the computer to say, okay, I saw a fringe, how long was it since the last one? And that gives us our time and distance pairs. We also get analog signals in, such as temperature and spring position, and there's a bunch of other things that you can measure and record through the computer. There's some other connections. Super Spring has to be connected to the sim for control. We'll get through later today. We'll get all that hooked up. A quick overview of the software. It's a Windows-based package, and then I swear we're almost done. Windows-based package, very user-friendly, lots of options. Each project, so the whole thing is a project, consists of individual sets. Each set consists of a bunch of individual drops. So you'll hear me talk about projects, sets, and drops. That's kind of the breakdown, if you will. So one green dot right there is one measurement. You can see here where they're taking 100 drops. Each one of these sets has 100 drops in it. This gives you a bunch of diagnostic tools and other stuff there. There are a few things that you have to put into the G software, site-specific data, latitude, longitude, elevation. Latitude and longitude mostly for tides and ocean loading. Elevation gives you standard pressure, and it's always good to know your gradient at the location. You guys do gradient measurements with the CG5? You done that before?
We got the Trident.
Trident as well. Very good.
Got that.
Okay.
So
Yep. Yeah. So then you just measure 3 different locations, go back up and down, and then you can get a good profile of how gravity changes over each point. This doesn't change, especially here in Louisiana where it's nice and flat. That's not going to change very much. Colorado, you got huge mountains on this, going up. So if you're further from the mountains, gradient's much worse. If you're closer, well, I shouldn't say worse. It's just different. At micro G, we're about minus 3 microgals per centimeter. Okay, so yeah, you'll see that. Yeah, so you should measure it. It's a good idea to measure it.
Elevation. I'm about convinced to start changing our reference to one of the international datums, especially in anticipation of the 2022 changes in NGS.
Okay.
But when it's in standard pressure, I'm wondering if is that something that's going to calculate, or is that do we need to be in the datum that the weather service is about?
That's going to be way more.
Because it's about 4.5 feet difference here.
Yeah, so it's 0.3 microgal. I think it's 0.3 microgal per millibar. So the pressure, the change in gravity due to pressure is very low, and the change in pressure due to elevation is even less. So this just has to be within a
It's
real rough.
Not a first term. So if it's that small, it's probably not significant, but we, especially from July, certainly the beginning of July through August, several, in South Louisiana in particular, we're really subject to squalls popping up, passing through, and there'll be a change in pressure as that goes through. Is that, because the instrument's calculating it, it'd be sensitive to that as it goes by?
Definitely, yeah, you'll see it. But there's also a pressure sensor, and so there's a barrel correction as well. So it accounts for that. It just takes the elevation and uses that for standards.
Standard.
Yep.
Okay, great.
Yeah, kind of a baseline. So, and then small changes again is,
But it's not something we have to report elsewhere, is basically what I was getting to.
right. And when we get things rolling, I'll show you where you put in the elevation and then you just hit set and it changes the standard pressure automatically. So, yeah, gradient is going to be, so gradient and lat long is going to be a much bigger effect for sure.
How
So.
precise do we care about the height of the point of measurement in the FG5X relative to the mark over which we're saying this is the gravity at that point? How precisely do we care?
Again, it's going to be kind of to the level of what precision you want of your measurement, right? The gradient is 3 microgauss per centimeter. So if you're 1 centimeter off, you could be 3 microgauss off. We will measure, so most heights are already known and very standard on the FG5, and I think I get into it. Yeah, perfect. So B and D don't change. That's very well known. That's from the factory. That's just a stack up of the super spring and the interferometer for B, and then the dropper height for D. The ones that change are A and C, and that's what these tools are for. This guy you put on the tripod and you drop the stick down, and then you know that will give you A.
Great, yeah.
That's your A. And then this one, you stick up underneath the tripod and you touch it to the bottom of the dropper, and that gives you C.
So in addition, if we've got, say, a domed monument, we would also see how high it is above the surface that we're on.
Right, so transferring your gravity measurement to a known location is easy in G in the software as well. You just tell it where you want to transfer it to. But yes, you have to be able to measure. So if it's domed, if it, let's say it goes, I'm not sure what you mean by dome, like if it kind of domed like that.
Benchmark.
Yeah,
It's got a little dome on it so your level rod doesn't hit the ground.
sure. So you can put this right over the top. There's a hole in the bottom of that tripod. Put that right over the top of the dome. Drop this on
Oh,
top.
in the center.
Yep.
Perfect.
Drop this right onto the
Oh.
on the thing. So yeah, transferring it to the mark.
I saw that.
Ideally, it's right over the mark, and you just drop that to it. But then, yeah, as far as weird, different.
The question came because I thought you were measuring it on the outside by the legs,
Okay.
and then we transfer it to the middle.
No,
Okay.
yeah, there's a hole in the middle of the tripod, and this drops right through it.
Perfect.
So, yep. Sorry, my confusion.
No?
Maybe I back up just a little bit.
Anyway,
Data acquisition parameters, you can also set
Yeah,
these.
forward motion.
Polar motion. The pole wobbles around.
I get notice once a week from DC as well as Paris.
Okay, so yeah, we post these on our daily updates on our website. If you just go to microglacoste.com, support polar motion. It used to be on the front page, but somebody redesigned the website, so you got to kind of search for it. But yeah, microglacoste.com, up top support polar motion, and then those are posted daily. Probably weekly is good enough. I don't know the change in polar motion to gravity. I don't know that off the top of my head, but it does matter depending upon where the pole's pointed. So,
Right.
and there's location in the software.
It's significant for second order azimuths.
all right.
So it's an area of about 100 meters at the North Pole. There's a spiral.
Yeah, and how it relates to gravity, I can find that out for you. The other parameters.
Probably changes in centrifugal forces as that pole moves around. It's almost like changing your latitude.
Mhm.
Okay.
Put these in, so you can change the number of drops per set, the number of sets, interval between drops. This is all just kind of internal to the software that set up your project. We kind of just have a standard with FG5. We do 100 drops per set. And depending if you're doing a short-term measurement, a lot of times we'll do 24 sets spaced out over a full day. The nice thing about that is if there's any tidal signal in there, you can see it, and it kind of cancels itself out. It does correct for tides using your latitude and longitude. But
Is there a default setting more or less that it wakes up
Right.
and it's probably trustworthy?
yes, yeah, absolutely. Yeah, so we run these. The last thing we do with this before we pack it up is run it for straight 24 hours, once every hour. I'm sorry?
Time. Oh, start time of data acquisition.
Yep.
Okay.
So you can delay it. Time it gets from the computer clock, just like actual time to set the blanking, the tides. Thank you. So I mean that's going to be crucial, right? What time of day it is.
Right.
That comes from the computer clock, and so we set that to UTC. You definitely need to make sure computer clock is accurate. If it loses power or somehow the clock slips, you need to update that. I'm sorry?
Get to the internet before you run.
Right. Yeah, we turn off the internet update though, just so that it doesn't try to reboot when you like in the middle of a project. It's like, oh, I have Windows updates.
Oh.
Reboot. Oh shoot, lost half my data. But yeah, you can update the time through the internet, and it should be good. But definitely, you need it within a few seconds, tens of seconds, but you don't need it better than really that. So, yeah, through the computer though. Start time of data acquisition, it refers to the fact that you can actually delay the start. So if you're like, well, I gotta leave, but I don't want it to start until 5 p.m. tonight because it's gonna get quiet, you can delay the start. I don't suggest doing that just because it's bitten me before where I set it up, I think everything's running great, but I forgot to pull the alcohol pool out, and now the beam doesn't get to where it needs to get, and no fringes. Yep. And so that, like, you come back the next morning thinking you have a night's worth of data, and you got nothing. It says, "Hey, I got no fringes." You have an error message up there. And you're like, "Oh, it's the alcohol pool." So I would say hit start, watch it drop for 10 drops, and then take off. Worst case scenario, you just chop off some data in the beginning and you move on. So, and then projects, yeah, we talked about how those are sets of sets. So, kind of got ahead of ourselves.
You just said something that's intriguing. Is it that easy to edit your data set?
Yes.
So you can say you truncated the first hour or whatever?
Yeah, so you can do as simple as just unchecking. So each one of these is a set.
Okay.
And you can, in reprocessing, it could be as simple as unchecking those. There is a way to
get rid of a noisy set if it happens.
Right, and they're already, and we can, actually one of the talks later this week is on G specifically, so we get much more into detail.
That's fine.
But it's already weighted, so if the set scatter is much higher, let's say you get an earthquake, it's actually weighted less than a much quieter set.
Excellent.
So the statistics are already done for you inside of G. That's one of the major benefits, real-time data acquisition, but you can also post-process. The number it kicks out here, you could write down and call good. It's really powerful. It even gives you the uncertainty of that project. Yeah, sorry, it's a blurry picture.
That's the final gravity estimate.
Yep. Yeah, so here, it's 979-622-836. The funny thing is I know that that's at our old building. You start to recognize locations by their gravity value, so. Yeah, so that's where we go with that. I think that answers the question.
Fine, thank you.
Gravity corrections, we talked about a lot of these already. Earth tides, ocean loading, barometer, polar motion gradient, speed of light. It's all done internal to the software, and it's done for you. You can always pull these out and turn them off if you want, and only do it in post-processing. Do it by hand if you think that's fun. Again, you have to put in some values, like we talked about polar motion, you have to put in the X and Y polar motion every day or every week. And ocean loading and earth tides, you have to put in latitude and longitude, but for the most part, it does the calculation for you. Major error sources, verticality is the biggest one, and that's just an operator error, if you will. If you're one spot off, you'll see what I mean by one spot. When you look in the scope, you'll see the beams, and if let's say those two beams are not touching, that means you're not vertical. It's 4 microgals, and then it's actually non-linear, so as you get more and more off, goes the other way though. So a little bit off gets you, half a spot is like 2 microgals, 1 spot's 4, spot and a half is 5, 2 spots is 5-ish. So as you get further and further away, it's not quite as bad, but definitely want to make it vertical. Water table, I don't know if I'd consider this an error source. I mean, for some people, that's what they're actually measuring. But 1 microgal for every 2.5 centimeters of water. So 1 inch of water gives you 1 microgal.
Water where?
Underneath you, overhead.
Are you talking about the depth of the water table?
Distance, not as much. This is volume. So like one spring in Colorado, we saw gravity overnight just jump up by 4 microgals and hang out there. We had a wet, heavy snow that night, and we went up on the roof and we collected like a core sample, like very unscientific, just took a beaker and flipped it up right side up, let it melt. So we saw 4 microgals and we had about just over 3 inches of water. And that's a huge error source in the,
That's cool.
and actually, sorry, it went down because it was overhead. So.
I remember for years at the University of New Orleans, when they first started taking observations for me, Sasagawa and then Winchester, I put in a water table well, and weekly I had a technician
Measure it.
get me depths of the water table, and they were correcting for it in New Orleans.
Yeah, absolutely.
For years.
But when in the term water table, are we talking about the traditional term that if you go down this far, your water is going to be found underground, or are we talking about a table that tells us something about water?
No.
Oh, no.
Underground.
We're
Yep.
talking about the depth
Yep.
of water.
Yep.
Okay.
Yep. Yeah. So this assumes an infinite plane, and it turns out it's 1 microgal per inch of water, basically. So, if it rains, ground gets saturated. In Colorado, we'll get big heavy rains and then nothing for months, and the ground just dries out. And definitely seasonally, we see it go up and down. Derek has a nice plot and he can predict what his gravity is doing up at Table Mountain.
Trying to figure out how I determine the water table at all the different sites.
Why are we going to need to buy a drilling truck?
Microgal per inch. And I would say from summer to winter here, depending on once you get away from the coast, the water table changed a lot.
I mean, that's what a lot of like USGS projects, they're measuring water reservoirs. I know they've got a project down in Arizona somewhere, just constantly measuring a reservoir and watching how it goes up and down and where the water's going and where. So
I guess if you got a high water table, it increases your gravity.
Yep, more water. Yeah, if your water table goes up,
Yeah.
yep. That's why when the gravity actually went down in my
Because we have
example.
high humidity, as we discussed earlier. And so I don't see humidity as an error source. Is that enough water to worry about?
I haven't thought about that. I don't have
They've
a
got, like,
thought of that.
Those twin sphere gravity meters
Okay.
that stay in place, and they say that you should run it for 5 to 10 years to figure out what the local systematic area is before you can rely on anything.
That would be my suggestion.
Run it for
Similar
5 or 6 years.
similar to that would be like, if you think you have a big seasonal signal, you need to measure for a year and get that seasonal signal out. you know, we've been in our current building we moved out there in 2010 maybe, so we've been there for 7 or 8 years, and we have a time series for our peers. That's how we know, and usually it's pretty obvious after a year or 2 or 3. You know, you get some repeat data. You can
Just know where you are in your signal.
Yep.
Another question to follow on that, is gravity that you report to, as the gravity for this location, compensated by your knowledge of the water table? Or so it's a standard, or do you report the last measured, you know, this year it was low water table, next year it was high? Do I get 2 different numbers to report?
You mean, so like if it comes back for service?
As, for instance, an official gravity report for this site.
Yep.
Which number do I record?
Oh, you're
Or
saying
do I
for
standardize?
you. That's more of a science question. I don't know. I wouldn't know how to. I don't know the answer to that. Yeah, it would be. I think you probably
I'm in the
contact
procedures
the. Yeah, for sure. It's big. I would contact people in the industry. Yeah, I would contact Derek just because I have better experience. Well, more experience with Derek. But yeah, he loves talking about that kind of stuff, and he'd probably have some good suggestions for you. Tim, yeah. Tim actually stepped away from Micro-G beginning of this year.
Oh, really?
Yeah. So he's doing surveying. He started.
He was the one who talked me into buying this thing.
Oh, really? Good.
I
Yeah.
was thinking A10. He said, no, we need this.
Yeah. If you have indoor sites that are, you know, well protected, and FG5 is better. So it's more accurate, and the A10 is more portable. And if you're doing lots of, you know, in a big field, you're doing lots of little points. You know, let's say you have a grid of 100 by 100 points or something like that. You know, take 50 points with the A10 and do the rest with CG5 or something like that. But for laboratory use, which it sounds like that's mostly what you guys have, that the FG5 is the best for sure.
Yeah,
So.
David had, to support his FG5, he had 3 A10s that he brought with him, and he used them to fill in the gaps in indoor spots. But then when he was doing gradients and all, he used the CG5. He had a truckload of gravity meters.
Yeah, no, it's we had a survey department, and that's kind of what Tim spun off and took. That they would go to like all over the world, different oil fields and injection sites and stuff like that, and measure mostly with the A10. We need some really good kind of main sites to calibrate the A10, if you will. It's an absolute meter, doesn't need calibration, but you want to be able to transfer that point, that measurement out to the field, and then fill in with a relative meter that's quicker. So I don't remember how many points, A10 points they did out. Like they're up in Prudhoe Bay, they've been to the Middle East, they've lots of big stuff, but so. Yeah, as you mentioned, Tim, this paper is great for air sources. You can find that. I think what's his name?
Sasagawa.
Sasagawa. I always stumble on it, I don't know why. I think he's on this paper as well.
Reference be in here somewhere?
That's the user manual? I'll definitely give you guys a copy of this presentation as well. But yeah, that's a good paper for specifically air sources of the FG5. So, talked about this a little bit. The only ones that change, A and C, B and D are factory standards. You get the actual height, kind of the measurement height, by adding all those up. We give a 100 centimeter mark. That's where we transfer to in our lab, just because it's halfway between the FG5 and the A10. The FG5 is about 130, the A10 is about 70, so we transfer to 100. You know, we're not doing core site markers on the floor or anything like that. We do have markers at each of our pier, but they're not, you know, we haven't done any like leveling or anything to them. So, so yeah, depending upon what your surface looks like and what your purpose is, I think most people report to 0. So that's all easily changed inside the software as well. So you can say, what's my transfer height? And
So if your A or C changes, T1 and T2 change.
Yeah, yep, absolutely, yep. Yeah, and so, correct, but your transfer height doesn't. Transfer height always, you'll either transfer to 100 centimeters or you'll transfer to 0.
Oh, this is what it becomes, okay.
Yeah, so we measure your measured height, right? So your actual height does change with A and C. And that will affect what your transfer, how much you
What
transfer.
you're calling transfer would be what I might have called the reported height.
Exactly, yes. Yeah, measured up from the ground. So ground is always 0. This is roughly 130. The A10 is roughly 70. And sometimes we'll, like in our lab, we transfer to 100, just halfway between. So. All right, we're just, last few slides here, just tying up some loose ends. We actually pre-scale, which means we don't take every fringe. We'll skip a bunch of fringes. We'll skip a known number of fringes. So in this case, it's kind of showing an example of we're only going to collect 700 time distance pairs. At that point, it could be as many as 700,000 fringes, right? Our drop length is 30-some centimeters, and you get a fringe every half wavelength, which is 300 nanometers. So in that full drop, you get a lot of fringes. So we skip a whole bunch. So this is the recorded number of fringes. You can see the actual number of fringes that went by, and then the time and the actual distance. I guess it's 210 centimeters for the FG5. I think the FG5 X is 245, something like that. Sorry, 210 millimeters. Yeah, and this basically is just so that you don't have huge files. This can all be changed in the software. If you want a huge file, you're more than welcome to collect all those. In the past, it was because computers couldn't handle it. It couldn't read that fast, and it couldn't store that much information. It's getting to the point now where you could record almost all the fringes, and it all gets saved into a text file. So it's, it's pretty small. They're pretty small files anyway. So one of the things that G reports is the fit residual. You'll see a squiggly line. The green line is the residuals. And what that is each one of these time distance pairs, so you'll see time here, distance here, gets plotted, and those are the red lines, or the red dots.
That's cool.
The blue line is the equation, basically. Perfectly known what gravity should be, what the trajectory, what the test mass path it should follow over time. And then for each red dot, we take the difference here. So here it's a little bit low, and we plot that here, and you end up with what we call the residuals. Mostly for diagnostics. Normal residuals are approximately 1 nanometer. So at any given point in the drop, the test mass is 1 nanometer from where we think it should be. So pretty accurate. But this will tell us, like if we look at the residual plot, it'll tell us, I think we have a picture back here. Yeah, so here's the fit residuals. This I think is nanometers. We're looking at like 2 here. So this one's not great, plus or minus 2 maybe. But this will show us, like if we see a big sine wave in it, it's probably a vacuum issue. Maybe you lost vacuum. If there's a big spike, so it could be hitting the side of the cart, that kind of stuff. So residuals are great for troubleshooting. Statistics, nobody likes statistics, but this tells us, you might ask, how much data should I take, right? And it really is going to depend on your site and how noisy what your drop scatter is. So your drop scatter here, your statistical uncertainty is your drop scatter divided by the square root of the number of drops. That's why if we do 100 drops, it makes the math easy. So if you have, if you're doing 100 drops, square root of that is 10, and let's say your scatter is 100 microgals. 100 divided by 10 is 10. Your statistical uncertainty is 10 microgals for that 100 drops. And then it quickly goes down as your set scatter goes down. Or it goes down not as quick as your number of drops goes up. And then you add that in quadrature with the systematic uncertainty. That is just from all your unknowns. Barometric is kind of all these errors that we were kind of talking about before. There's an error on earth tides. There's an error on ocean loading. Your verticality, hopefully you're closer than, one spot off, but there's also a place that you can add that into. Sometimes if it's really noisy, the beam as you're trying to make them vertical is bouncing all over the place. And
Kind of like an old-timey G meter.
yeah, exactly. So you have to do your best, and you could say like, well, I think I got to within one spot on that location. So you add this into your, 4 microgal error into your systematic uncertainty, and that there's places to change all that inside G as well, and that gives you your total uncertainty. So pick your desired statistical uncertainty, knowing your drop scatter, and then that determines your number of drops. Spread it out over 12 or 24 hours, and that way your whole project gets you down to the level that you want to be at. This is getting less important. The balls and V's, we're designing the dropper to catch better. The balls and V's are just more robust, using different materials and that kind of stuff. But it is true. I mean, every drop you do pounds those balls and V's, so run only as long as you need to, and then it won't have to come back as often. We definitely don't see as many issues with the FG5X for lots of reasons. So.
I remember that first time at the University of New Orleans, they were there for 4 or 5 days.
Yeah.
Just running continuously.
Yep. There's some groups that run a lot. Depends upon what signal you're looking for. I know there's a couple Japanese groups that look for like CO2 sequestration and injecting it into the ground, and so they're looking for small changes over a short period of time. So they'll do the same thing, like back-to-back sets over 24 hours, and you maybe collect 10,000 drops in 24 hours, and just because you want to see that signal of gravity going way up or whatever it might be, or fluctuating. So definitely not. This is the intention of these meters is not as a relative long-term monitoring system, such as like a G phone. I don't know if you guys looked at the G phone. It's just it's a relative meter like the CG6 or CG5, but it instead of taking measurement, it just real-time, long-term. Set it in the back of your lab, watch gravity drift around. Maybe a superconducting gravity meter. Have you heard of those? We'd like to think that we compete.
That's what I was talking about, the spheres.
Okay. With the helium, the super cooled.
Yeah, niobium spheres in liquid nitrogen superconducting.
Okay. Yep. Yeah, I didn't know there were 2 spheres. I don't know the.
1 or 2.
Okay. Yeah, I didn't know the mechanics of it that much, but we like to think that the G phone competes with that, just because it's smaller and more portable, cheaper, but gives you the same quality data, long-term monitoring kind of thing. So a lot of people have either a superconducting gravity meter or a G phone in their lab, and that'll give you that signal that you're, like kind of the seasonal signal you'll see in the relative data. Or if something comes overhead, you'll see gravity change, and then you'll know with your snapshot, your absolute snapshot, you'll know kind of what gravity's doing. So, does this kind of make sense? I mean, it's kind of just tells you, depending on your drop scatter, that'll tell you how many drops you need to take in order to get your statistical uncertainty that you want.
You do a test set or something to figure out what your spread probably is, and then I'll have sufficient drops over this period?
Yeah, I think that would be a good way to do it. You could just run for 50 drops. 10 drops might get it, but you can get at least a good idea of what your drop scatter is going to be.
Sets you want, how long?
Mm-hmm.
Okay.
Yep. Kind of this, just going back through this math, roughly 2 microgal systematic uncertainty. Got a drop scatter here. It shows you in this window 15 microgals. To get to 2 microgal systematic or statistical uncertainty, you need about 100 drops. So 15 divided by 10 gives you 1.5. So you're at 2. Yeah, if let's say you're, oh, sorry. Let's say you go to a different site and it's 100 microgal. Yeah, you're going to need 2,500 drops total. This is more for the FG5. FG5 X probably 500,000, so you could do twice as many. So you could maybe do 200 sites at that level. Again, it depends upon how noisy your sites are, as well as tuning matters a little bit. Like, if your dropper is just slamming that test mass every time it drops, that's all set at Micro-G. But if you start to hear it, hitting really hard, let us know, and we can change some tuning in the hardware and get it back to running. So you'll know when we lift and drop, you'll hear it, and you won't hear anything, and that's the way it's supposed to be.
Yeah, I could definitely hear David's FG5 working.
Yeah.
Yeah, once a second you could hear.
So you doing the FG5 or the A10?
That was FG5.
At a second. It's pretty quick for
I'd say a second, but there.
a few seconds. Yeah.
Yeah. I could hear it. It might have even been 10 seconds. It was quite.
Yep. Yeah, so you might need some dropper tuning. The FG5 is a little bit, it's not as smooth for sure. You can hear it moving around more. The FG5 X is smooth. It's really nice.
Oh, good enough to hear.
Yeah, exactly. Yeah, regular maintenance at Micro-G we talked about a little bit. 500,000, maybe upwards of 1 million drops. The nice thing is, especially if you're doing field work, optics, we clean all the optics. Replace the ferrofluidic feed through if need be. So there's a motor that goes through, and you have to be able to get in and out of the vacuum and maintain vacuum. I'll point that out when we look at the dropper a little bit more.
What is ferrofluidic?
It's a
It's a
magnetic fluid. Mm-hmm.
What's its purpose?
To just basically be able to get mechanical movement through the wall.
Using it for hydraulic?
It's the dropper. So sorry, it lifts and drops.
Okay, now I got it.
The dropper. So there's a motor on the outside that spins the ferrofluidic feed through, gets into the vacuum, and then spins a pulley that lifts and drops the
Get through
cart.
Perforation.
Yep. Yeah, it's just a feed through. Ion pump. Yep. It's throwing molecules into the plates, and it gets plated, and so it only has a limited life. That needs to be changed out once in a while. That can be done on site. Ferrofluidic with the new one, with the FG5 X, not as easily. That one's pretty tough with the FG5 X. You have to take the glass off and get down in there and loosen stuff up. But definitely the ion pump is just 6 bolts on the outside. Put a new gasket on there, slap the new ion pump on there, and make sure you get everything tight. And then turbo pump it for 12 to probably 24 to 48 hours at that point. Dropper belt wear, you'll see the belts in there. They just go up and down, and they bend and unbend and bend and unbend. So that's probably the first thing internally that will break after 1 million drops or so. Again, we had one at Micro-G that had over 1 million drops, and we're just starting to see some sign of fatigue and failure in the belts. So balls and V's do wear. The indication there is that you start seeing in the drop profile, you'll see, I'll show you with the quad detector later this week, you'll see the test mass rotating or translating. And that's just because one ball or V is worn down and sticky and gets hung up and pulls the test mass off. Those have to be replaced at Micro G. And then the laser tube, either the helium, I mean helium's hard to keep in anything, so it just leaks out, and so you'll see power over the years go down. It's probably 3 to 5 year kind of thing. You're looking at a new laser tube there. We don't usually see problems with the iodine cell. It's almost always the helium. I'm sorry?
It's passive, isn't it?
It's mostly just because it's easier to keep iodine inside.
Oh,
The helium neon tube, the helium just almost no matter what you do just gets out, and so that's how you lose power with the in the lasing part of it. Nice thing about that is it's pretty easy just to send the laser back to us, and so that transportation, the cost is a little bit lower. So good excuse to go to Colorado though. Applications, we talked about a bunch of applications. I know everybody's getting tired and hungry. So, I mean, we could talk more about this stuff, but it sounds like mostly you guys are probably more focused on the geophysics, maybe a little bit of geodesy. But there's kind of a quick list of things a lot of our customers use it for. I might just kind of go through quick results. We talked about the comparisons. Oh, this is the next slide. Okay, yeah, there's been multiple comparisons in Luxembourg and throughout the world. This is just kind of a plot of this one time. This is a new system out of, I think, Italy, and they were still working on it. So this is not one of our systems, but you can see the FG5s just within a few microgals of each other. Gilla G was the predecessor to the FG5, and then the A10, bigger error bars, but still the error bars hit pretty much in the average. This is the mine in Luxembourg. It's actually in the back of an old basalt mine. They have this nice lab. It's really quiet. You can see all the FG5 set up here and a couple more in the foreground. 20 gravity meters. There's also been, so that's the European comparison, the international comparison, and the North American is the one that is in Boulder that Derek's trying to do on the even years. I just like Luxembourg, Paris, Beijing, Boulder. Oh, that other picture didn't come in. No. There's another picture here of actually Boulder. This is the last year in Luxembourg that we did it. We had to move to a different lab. We couldn't go into the cave because it was falling apart. It was about to collapse. I was like, okay, it sounds good to me. But it's over 2 weeks usually. We got 20 plus groups come in with FG5s. Everybody gets together and make sure that they get the same number. So it's kind of time series. This one started with the Gilla G, and then this was done with an FG5. You can see here, I think this is due to a post-glacier rebound.
Cool.
So, yep, as the
Opposite problem.
we've got that too.
yeah,
It
goes the other direction. As the glaciers melt, the water comes up.
Yeah, Gulf of Mexico's heavy.
Yep. Yeah. Oh, and it pushes on the ground. Yeah. Yeah. So you can see the trend early on. Quite a bit of scatter in the earlier meters, but if you plotted a trend through those few data points, you get something. And now with the FG5, just nail in the rebound. Is that Churchill up in Canada? Yeah. So stuff you can do. Thank you.
What the hell is nice to take a gravity reading?
Yeah. Yeah. All right, I know that's very dry. Sorry, gravity's not.
I'm sorry? On the number of drops before it has to be sent for service, is there somewhere in the software that keeps up with the total number, or do you have to know your projects and how many drops for each project and manually know how much you're doing? It's not there's not like an odometer anywhere that tells you you're at a million.
Nope. No, you'll have to, in each.
What you need is a cold chisel and just make the marks on the loading dock.
Yeah, in each set file, so in each project, it makes a folder. There's a text file that tells you kind of how many drops in each set and how many sets you took. So it's pretty easy. I mean, you have to go back through data, but it's pretty easy to find that information. And there's no set number. Like once you hit 500,000, it's not like, all right, ship it back. Don't do another drop. It's kind of, it varies from system to system a little bit.
What symptom would you look for first? Obviously, between 500,000 and a million is a big span.
100%.
What symptoms would you expect to see that says, "Ooh, maybe I want to send it back"?
So you'll see, like your drop scatter will go up, and that means maybe there's something going on with the super spring, as well as the dropper. You know, we talked about the balls and V's as it rotates. Sometimes it translates or rotates a little more, a little less. So you'll see your drop scatter go up. There's actually a window in the software drop histogram that'll tell you a lot. You know, it should be a nice even distribution about the average.
So you'll see that kind of change either in variability or the change in the shape of the normal curve.
Right. Yeah. So drop histogram, your fit residuals, your fit sensitivity. I'll go over that on the next couple of days after we get some data. Those are diagnostic tools to tell you if the system's running well or not. But it can be subtle. It really, I mean, you know, if something little is off, it could be, you know, it could make a change in gravity and not notice it. So pretty much anything you look at on the software should be a flat line. And if it's not a flat line at that point, yep. Yep. So, good question though. It is hard to tell.